To everyone. Welcome to the week number 4 of the live problem solving sessions for the course on traffic engineering. I am Sedu Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's start with an overview of the content for week 4. Okay, so this week, we were looking at analysis of freeways, multi-lane highways, as well as the two-lane highways. What were we analyzing? We were looking at how to characterize these, facilities in terms of their level of service, right? So we want to analyze the level of service and capacity of these different facilities. So the first lecture, we were looking at some basic concepts, right? So what do we need to know? So we need to know about capacity, right? So that's one of the things that we are analyzing, and the quality of service and the level of service, right? So as we saw in the in the last week also, we were looking at what capacity is. So what is capacity? It's basically the maximum flow rate, maximum sustainable flow rate, over a period of time that the facility can support, right? So that's what capacity is. So this is different from the volume or the demand, right? So which is what demand is basically the number of vehicles or person that wish to utilize that facility, whereas capacity is from the supply side is what the facility can support, right? So so we looked at next the quality of service and the level of service. So quality of service is basically the user's perception. Who are the users? The users are the travelers, right? So who are using the facility, how do they perceive the quality, right? So and how do they do it? So it's what people, when people drive, so what they see is the speed, right? So if the speed is too low, right, so you can't drive faster, so you will feel that the facility is not good enough, right? So or if there are long queues, right? So or if it takes a long time for you to travel, so all these affects the user's perception of the quality of the facility, right? So that is the quality of service. And the level of service is how do we capture this quality of service, or how do we quantify this quality of service, right? So because the user's perception of the service quality is a qualitative one, right? So it differs from each person to person, right? But the level of service is a quantitative measure, right? So we try to quantify the quality of service through LOS, right? So for this we come up with certain measures, right? So performance measures. So to to evaluate the service, right? So how do we do this? So we look at different performance measure, like what is the average travel speed, what is the density, right, and so on. So there are different measures that we use for different facilities, and then we come up with a way of so depending on the values of this measured quantity, so we try to characterize the level of service of a facility, right? So finally we come up with a level of service from A, B, C all the way up to F, right? So we'll have 6 different levels of quality, right? So A being the best and F is the worst. Okay, so we try to do this for different facility, and one important thing is this LOS definition, or this scale that we say A to F. So this is not constant or universal, right? So it changes from the facility to facility, and also depending on the mode that is being analyzed, right? So even though the scale we say it is from A to F, so what is level of service A for a freeway will not be the same as what is the level of service for say a two-lane highway, right? The speeds, densities, everything will vary. So it is dependent on the facility and the mode that is being analyzed. So in the next lecture, we were looking into freeway and multi-lane highway segments, right? So this is so first we are looking at these two, and because the method that is used for analyzing these two facilities are the same, right? So we consider for this analysis these two to be uninterrupted flow facilities. So why? What is uninterrupted propensity? So we saw in the initially we characterize these into two categories, right? Uninterrupted and interrupted. So uninterrupted means there is no external factors that affect the flow of traffic, right? So other than the traffic stream itself, there is no external factors like signals or intersections, that will affect the flow characteristics. So even though in multi-lane highway we can have certain locations where there will be intersections that can affect the flow. But if we look at segments which are apart or away from these points that can affect the flow, majority of the times we can analyze those segments as uninterrupted facilities, right? So that's why we group these two together and then try to analyze them together. So in that we were looking at different flow characteristics, right? What are the different flow characteristics? So we have under saturated flow. So what is undersaturated flow? So undersaturated flow is basically, so when you have basically demand is less than your capacity, right? And also this is not this demand is not affected by your any incidents or any other bottlenecks that are present downstream, right? So flow is taking place without any interruptions. And then we have oversaturated conditions, right? So this is when your demand exceeds capacity, right? So when bottlenecks are created, so the facility is not able to cater to the demand that is wanting to use the facility. So your level of service goes down in those situations, and that is oversaturated condition. And then we have also Q discharge, right? So this is like intermediate, right? So so when you have oversaturated condition, once the bottleneck clears, the queue that was accumulated will now start accelerating, right? So from the oversaturated condition, it will start moving towards the unsaturated condition, and the flow that you will see in those time is the queue discharge, right? So this will not be in the undersaturated flow, but this will be approaching that, right? So it is somewhat lesser than what was there before the oversaturation took place, right? So like this, we characterize flow into different categories, and then we looked at capacity under the base condition. Right. So when we are looking into analyzing capacity, first we define what is the initial or the ideal capacity, right? So what is this? So base condition is basically, ideal conditions. So where we assume the weather is good, the road condition, the pavement condition is good, there is no presence of heavy vehicle, nothing that affects the flow, right? So everything is, perfect, right? So that's the base condition. Under that base condition, what is the capacity that the facility can provide? So that is the base capacity, right? So this gives us the base capacity. And then all that we do is we take this base capacity, and then for the existing conditions, right? So I said the base capacity is based on ideal condition, right? So but in reality, the ideal, the existing condition or the prevailing condition will be different, right? So so for the prevailing conditions, we try to adjust this base capacity, right? So we will have adjustment factors for different for violation of different conditions from the base condition, and then we try to come up with what is the capacity under the existing condition, right? So that's the idea. And then the free speed flow relationship was also discussed. So what is the speed flow relationship that we have for freeways and multi-lane highways? So we'll have something like this. So we have the speed and we have the flow rate. Okay, so the relationship is something like this. So you'll have a constant speed. So speed does not immediately drop as flow increases. So it will remain constant until some level of flow, and then once a certain level of flow has been reached, any further increase in the flow will start lead to sharp decrease in the speed, right? So this is not linear, so this will be a parabolic decrease. And this point, where the speed suddenly drops, so that point is called the break point, right? And this constant speed that we call as the free flow speed, right? So which means there is no the existing traffic, the stream, the vehicles in the stream, they are not influencing each other. So every vehicle can travel at the maximum speed, which is the free flow speed. But once a certain level of flow has been achieved, right? So after this, the vehicles will start interacting with each other. They cannot flow freely at the same speed, and then suddenly they will start the stream velocity goes down, right? So this is the break point, right? So that's the relationship that we have between the speed and flow. So next, in the second part of this analysis in lecture 18, so we looked at what are the different LOS criteria, right? So because for because LOS finally outputs a qualitative value, right? It's one value between A and F, right? But to come up with this qualitative value, we need some quantitative measure, right? So for example, we look at density, right? So if it is between A and B, it is level of service A. If it is greater than B, less than C, it is level of service B, and so on. Right. So that's how we come up with. So what is this criteria, like density or whatever it is, the measure that we use to come up with this categorization. So those are the LOS criteria. So we looked at what is that for the freeways and the multi-lane highway. Basically, we look at the density for freeways and multi-lane highways. And the LOS classification, as we already looked at, is the 6 levels of classification. So A is the best condition, and F is the worst condition. So F corresponds to also the breakdown condition. So what is breakdown? When your demand V is exceeding your capacity, right? So which means the facility is no longer able to support the demand. So that's the breakdown condition. That is the worst case, F. And then we looked at the method for determining this LOS. So we have several steps. So first we start with finding the free flow speed, and then the base free flow speed, and then we adjust it to get the actual adjusted free flow speed, and then go through a series of steps to come up with the LOS finally. So we started with that, and in lecture 19 we continued it, and this methodology was discussed, and finally some numerical examples were provided. And with that, the freeway and multi-lane highway segments part was over. And then in the final lecture, we started or introduced the two-lane highway segment. The same analysis has to be repeated for the two-lane segments, right? So here again, we looked at what are the classification of this two-lane highway segments. Basically, we have three classification, right? Class 1, class 2, and then class 3, right? So we divide these into three classes. So class 1 and class 2 are basically in the rural, these two-lane highways passing through rural regions, and class 3 is for urban region, right? So why do we make this distinction? Because depending on this the location of their presence, so the expectation of from the facilities are different, right? So for example, in the rural region, we expect to travel a lot faster, right? So we do not have too many external influence, right? And also the flows will be low. So we expect them to have perform better in terms of whatever is the LOS criteria that we come up with than the same condition in the urban areas, because in urban areas we'll have a lot of side friction, right? So like in terms of intersections, signals and so on. So therefore, so we have two different ways of we look at them differently or analyze them differently. So we have three different classes. And then for these, what are the base capacity and the LOS criteria? So the LOS criteria varies for rural and urban routes, right? So we have three different criteria. One is the ATS, which is average travel speed. Then we have PFFS, percentage of free flow speed. FFS is free flow speed. And then we have PTFS, which is the percentage of time spent following. Right, so we do not use all these three criteria for all the class of two-lane highways, right? So for example, class 1, we use ATS and PTFS For class 2, we only look at PTFS, and for class 3, we look at PFFS, right? So depending on the type of the facility, the LOS criteria will also vary, and also the levels, the quantitative, the segmentation between the levels will also vary, right? So the LOS analysis is facility as well as the mode dependent. Okay, so that's what we looked at in week number 4. So now let's get into some problems related to these. So the first question. So here, let's start finish up. What we had last week. So where we are looking at queue length and delay analysis using the shock waves. So the first question is the southbound approach of a signalized intersection carries a flow of 1,000 vehicles per hour per lane at a velocity of 80 kilometers per hour. The duration of the red signal indication for this approach is 15 seconds. If the saturation flow rate is 2,000 vehicles per hour per lane with a density of 120 vehicles per kilometer and the jam density is 240 vehicles per kilometer, then determine the following. A. The length of the queue at the end of the red phase. B. The maximum queue length. And C. The time it takes for the queue to dissipate after the end of the red indication. Okay. So it can take like 5 to 7 minutes. Okay. It will take some time. So once you've finished, we can discuss the answers. Okay. So if you have any doubts or questions that needs to be clarified, you can ask. Otherwise, you can continue to solve it.
No doubt, sir.
Sorry, has anyone done part A? Okay, so here are the answers. So let's see how to solve this problem. So here we are looking at analyzing a signalized intersection, right? So we'll use the shock waves concept, right? So how do we do this? So basically, for shock waves, we are analyzing the flow of the traffic state in space time, right? So how the traffic states flow across space and time. So the y-axis represents the space, which is the longitudinal direction of the the road section that we are looking at, and the x-axis represents the time. Okay, so we have a signalized intersection. Let's say this is the location of the signal. Okay, this part. Okay, so what do we have? So we have a demand that is approaching this intersection, right? So that's what is given as 1000 vehicle per hour per lane at a velocity of 80 kilometers per hour, right? So there is some flow that is coming in. Okay, so this is at 80 kilometers per hour. Okay, so what happens? The signal, it's going to interrupt the flow, right? So at some point, it's going to turn red and then it's going to stay red. So this is your red duration. This is the red duration, so which is 15 seconds in this problem. Okay. So until the time it was remaining green, the vehicles can flow at this 80 kilometers per hour, right? So there is nothing stopping them. But once the red duration starts, now vehicle has to stop, right? So which means the speed will become zero, right? So that's why the flat line we have. So now what happens? So the flow that is taking place in this region, let's call this, traffic state A. So the demand, the inflow is still traffic state A. Even during the red duration, vehicles will keep approaching the intersection, right? So the traffic state is A here. But if you look at immediately, upstream of the signal, right, in this region, so what will be the traffic state there? Because the signal has turned red, the vehicles have to stop, which means jam conditions will occur, right? So there is zero speed, right, but no jam density because vehicles are stopped. So let us call this as traffic state say B. Okay, now because there are two traffic states, A and B here, right? So a shock wave will be created, right? Because in two traffic state meet, the shock wave is nothing but the boundary or the interface that separates these two traffic states, right? So what happens? There will be a negative or a Q forming shock that will be created, right? So this is a Q forming shock that separates traffic state A and traffic state B. Okay, so because of this, that Q length is growing. What is the Q length? It is basically how far from this signal location the traffic state B has grown. Okay, so this vertical distance between the signal and the negative shock, that is your Q length at a given time. So okay, so that is the state once the signal turns red. But what happens, this is not going to be existing for all the time. So it is going to turn green after some time, right? So this part, what happens when the signal turns green? So vehicles can once again flow. And what is the slope of this line? So vehicles will be flowing once the signal turns green. So vehicles can flow at the saturation flow rate. Okay, so this is speed corresponding to the saturation flow rate. Okay, let's call this as traffic state C. Okay, right. So we have traffic state C and traffic state B, and there will be a shock that will be separating these two, and that will be the Q backward recovery shock. Okay, right. So this is your recovery shock that is separating traffic state B and C. And so there is this region here. So what is the traffic state there? So this is the region during the red duration, right? So we know that traffic state B is jam density because vehicles are waiting there, queuing up there. But what will be the state immediately downstream of the signal? So this will be the zero flow, zero density, right? Why? Because no vehicle is crossing the signal, right, during the duration. So the flow is zero, right? So flow is zero, speed is also zero. So this is the zero flow state. Let's call this flow state as D. Okay. Yeah. After this point, so this recovery shock and the queue forming shock will meet at some point. So that's when queue no longer exists. Right. So after this, whatever vehicles are coming, so they will again be flowing uninterrupted. So until the next, red phase starts. Okay. So that's what happens in the signalized intersection. Now, what are we asked? So we are asked to find the length of the queue at the end of the red phase. Right. So what is the end of the red phase? So this point, let's call this T1. Okay. So let's assume when the red starts, that is our origin. Okay. So this is time 0. And we'll also keep x to be starting here. Like the signal is at location 0. Okay. So when red starts, time is 0. And signal location is our location x is 0. Okay. So with the so what is the Q length at the end of the red phase? So this is basically the length, this particular length, right? So wherever this Q, forming shock is present, at T1, right? So that is that distance from the signal is the length of the Q, right? So how do we find this? So we for that we need to know what is the equation of this particular backward forming shock. Okay, how do we find that? So this the slope of this line is nothing but the speed of the shock wave, right? And we know how to find the speed of the shock wave, right? So given two traffic states A and B, right? So how do we find it? So the speed of the shock wave that is separating A and B is nothing but QA minus QB by KA minus KB, right? So Q is the flow and K is the density, right? So this we saw last week. So if we know the flow and the density at the two traffic states, then we can find the speed of the shock wave. So we can get the slope of this line, and we also know the coordinates, right? So with that we can get the equation of this line, and then we have to find out when what is the point it reaches when the red duration ends. Okay. So how do we do this? First, let's get the slope of the line. The slope of the line will be what WAB is. So what is QA? So A is nothing but the inflow condition. So which is 1000 vehicles per hour. Okay. What is QB? B is the jam condition, right? So which means there is zero flow divided by, so Ka minus Kb. So density. So what is density? We don't know the density, but we know the speed is 80 kilometers per hour. So that is given in the question. So density is nothing but Q by V, which is the speed. So Q is 1000. So V is 80. So this is 12.5 vehicles per kilometer, right? So that is the density at state A. Okay, so 12.5 minus what is KB? What is the jam density? The jam density is given in the question as 240 vehicles per kilometer. So minus 240, right? So what is this? This will be minus 4.4. Okay. So why is it negative? Because this is the backward, forming shock wave, which means the shock wave is moving, against the traffic flow, right? So it is moving in this direction, downward direction, right? So which is, in the upstream direction. That's why the slope is negative, which means it's a backward moving shock wave. Okay, so which is minus 4.4. Let's write the equation of this. That backward forming shock wave. So that is x is equal to minus 4.4 t, and because we have assumed this, this point to be the origin. Okay, so there is no constant here. So this is the equation of the particular backward forming shock. So what is the q length? So now q length is nothing but whatever is the value of x at time t equal to 15 seconds, right? So that will be the point, that will be this particular point, right? So let's say x 15. So x at 15 seconds is nothing but minus 4.4 into 15 by 3600, right? So units are important. So because what is the speed here? So speed is in kilometers per hour, right? So because our speed densities and the flows, are in the units using hours and kilometers, right? So therefore, our time axis, in the equation is in hours. So we have to convert 15 seconds into hours. So that will be minus 0.018 kilometers, right? So which means again here x is minus the length of the queue is actually the modulus of this. So length is 0.01. So Q length is positive. So this minus means it is in the upstream, right? So it is downwards in the upstream direction, right? So it has the Q grows to 0.018 kilometer length. When the signal just turns green. Okay, so that is at the end of the reference. So that is the first part. So second part is what is the maximum Q length, right? So if you look at the figure, we see that the Q still grows, right? So not growing, it's going farther and farther back, right? So at particular point T1, we found what is this, but it is still moving backwards. After some time T2 is when the Q is completely dissipating. Okay. So we are asked what is this maximum point? So where does it disappear? Where does the Q disappear? So what is that point? So to find that point, we need to find where this backward recovery shock wave is intersecting with the backward, forming shock wave. Okay, so let's just take a new page. So that is the signal. So you have so T1. So this was 15. Right, so this is here 0. This is also 0. So you want to find out T2 and also X2. X2 is what we want to find. Okay. So we know the slope of this line is minus 4.4. Okay. So now we want to find the slope of this line. So, but what is this? So this is separating traffic state C and traffic state, B. So B is jam density. This is saturation flow. Right. So and we know what the saturation flow condition is. The saturation flow condition is 2000 vehicles per hour at a density of 120 vehicles per kilometer. Right. So now we want what is W, separating the traffic states B and C. So traffic state B has a 0 flow. Traffic state C has 2000 and density at B is 240 and density at state C is 120, right? So which is 2000 minus 2000 by 120, which is minus 16.67 kilometers per hour. Okay, so that is the slope of the recovery shock. Okay, the recovery shock moves faster, that's why it is able to catch up with the backward forming shock and then clear the queue after some time. Okay, now we want to find the point of intersection. So the equation of the recovery shock is minus 16.670 plus some A because it's shifted, right? It's not starting, it's starting only at the end of the red duration. So A is, but we know this particular point is 15 seconds at location 0, right? So we can substitute that in the equation. So this will become 16.67 into 10 by 3600. Okay. So now we need to find out where these two shock waves intersect. So first shock wave is minus 4.40. The second shock wave is minus 16.670 plus 16.67 into 15 by 3600. So we want to find the intersection point. So equating those two, okay, so 16.67. So just rearranging the terms. Right? So from this we find what T is, and so if you solve this into 1 by 16.67 minus 4.4, right? So this is nothing but T2, right? So this is the point of intersection, and that is what we have represented as T2 in the figure, right? So this will be coming out as 0.0057 hours. Okay, so this is the time at which the two shock waves are meeting. But this is not what we want. We want x2, right? So what is x2? We can substitute back in one of the shock wave, because both of them pass through this point. We can substitute in any one of them. So we'll substitute in the easiest one. So x2 is equal to minus 4.4 into 0.0057. Okay, so that will be minus, that is 0.025 kilometers, right? So this is the maximum equivalent, right? So what was the equivalent at the end of it? So that was 0.018, right? But the maximum equivalent is little larger. It is 0.025 kilometers, right? So that is the maximum distance to which this jam density has traveled back, right? So up to this location the jam density has been reached. Okay, that is the second part of the problem. So third part is, what is the time it takes for the Q to dissipate after the end of the red indication. So this is simple because we have already solved for it, right? So we know T2 is 0.0057. But what is T2? T2 is from the start of the red duration, right? We have assumed red duration starting is 0. So from 0, it has taken 0.050057 hours. But the question is the duration from T1, right? So T1 is the time when red duration has ended. So basically what we want to find for that is T2 minus T1. So both points we know. So T2 is 0.0057 minus what is T1? Oh yeah, T1 is the red duration, which is 15 seconds. Okay, so minus 15 by 3600, right? So that will give you 0.0015. This is in hours, right? So this much time it takes once the signal turns from red to green for the Q to completely dissipate. Okay, so those are the three parts that were asked. Okay, any questions? Was the steps clear? Any doubts? Okay, so
No, sir.
okay. So the calculations are all simple. So basically, you need to just draw the shockwave diagram correctly, right? So once you have drawn the shockwave diagram for the given situation or the given scenario correctly, then all these slopes and equations you can easily find out and then get the answers. Okay, so just drawing this shockwave diagram correctly is the most important part. Okay, so moving on to question number 2. So you have to accept or reject the given statement. When traffic demand exceeds the capacity, observed flow equals the demand. So do you accept or reject this statement? So you can use the chat. You can put either A or B. Any answers? When demand is higher than the capacity, will the observed flow be equal to the demand? Any answers? Do you think the statement is correct? Okay, so the right answer is we reject this statement, okay, because that given statement is not correct, right? So what it is saying, it's saying demand is higher than the capacity, but flow is equal to the demand, right? So that's not true, right? So here we need to clearly understand what these three terms mean, right? So one is the demand, another is capacity, the third one is observed flow, right? So these three, represent, we are talking about, in all the three, the vehicles per hour, right? Some kind of flow rate, okay? But what it actually represents is different. So what is demand? So demand is equal to, number of vehicles wanting to use the facility, right? So how do we use? So use is nothing but passing through it, right? So how many vehicles want to pass through, use this facility and pass through, a particular location, right? So observed flow, so it's a measured flow, measured flow in the field, right? So this is if you go to the location, the facility, and then find and then measure it. So this is the number that you will see. That is the observed flow. And finally, we have capacity. Capacity, we know this is the maximum sustainable, flow by the facility. This is what that can be allowed by the facility, right? So we cannot travel at a flow that is higher than the capacity, right? So that's not physically possible, right? So this is like the physical limit to the flow, right? So here we are trying to, try to compare these three quantities. So so when you take a road section, let's say this is some two-lane road, okay, right? So after some time, let's say this is becoming a single lane, right? So there is a lane reduction, okay? So clearly you can see the capacities are different. So until this point you have a higher capacity, and then after this point you have C2, which is lower, right? So there is a clear reduction in the capacity, right? Suppose you are interested in this particular location, okay, and say 1,000 vehicles are coming, okay, 1,000 vehicles per hour. So that is the demand. So that wants to use the C2 facility as well. Okay. But because the capacity is reduced, let's say this can only support 750 vehicles per hour. Okay. So what will happen? So when you are standing at this location and then you are counting the number of vehicles passed, so you will find that there will be only 750 vehicles that are crossing this location. But what is the demand? The demand is 1,000, right? So because 1,000 vehicles want to pass through in 1 hour, but because the capacity is lower, right? So only a lower number of vehicles will be observed, right? So when demand is higher than capacity, right? So observed flow will be lesser than the demand, right? So but if it is the other way around, let us say if only the demand is 500 vehicles, right? So if only 500 vehicles are coming in and this facility can support up to 750, then what you will be standing here and observing, that will also be 500, right? Because 500 can be accommodated by this facility and only 500 are coming in. So which means the observed flow. So when demand is lesser than capacity, in that case the observed flow will be equal to the demand. Okay. So these are the two cases. But here we are talking about which case? Here we are talking about this first case when demand is exceeding capacity. So in that case, the observed flow will be lower than the demand. It will not be equal because the capacity cannot, sustain or support the demand, therefore the observed flow will be lower, not equal. That's why we reject the statement. Okay, question number 3 is determine the maximum queue length formed when an incident on a two-lane one-way road leads to the closure of one of the lanes for 30 minutes. Also find the total delay, the number of vehicles affected, and the average individual vehicle delay. So the capacity, the lane capacity is 1800 vehicles per hour per lane, and the volume, the inflow is 3300 vehicles per hour. Okay, take 5 to 6 minutes. Yeah, I'm just waiting for people to solve it. Wait for a few more minutes, and then once you have tried it, so we can just look at the answer. Has anyone solved it? So at least the first part, just the maximum queue length. Any answers? Okay, so we'll look at the solution now. So here are the answers. So we wanted to find the maximum queue length, total delay, total number of vehicles that are affected, and the average individual vehicle delay. right? So in questions, where you are asked to find the delay and the queue lengths, so it will be easier if you use the cumulative count curves. Okay, so what does those cumulative count curve do? So basically you take for the given facility, the y-axis gives you the cumulative counts. Cumulative count. So you will draw two curves. One represents the arrivals. How many vehicles have come to this point that you are analyzing. Cumulative number as a function of time, and then another curve for how many vehicles are leaving the facility or the point that you are analyzing. Okay, so we call them as the arrival and the departure curves. Okay, arrival curve, how many vehicles have entered, and departure curves, how many vehicles have left. Okay, these are the two things that we want to draw. So what is happening here, we are looking at a particular two lane highway. Okay, but what happens is for 30 minutes one of the lanes is closed, right? So which means there is a reduction in the capacity, just like what we saw earlier, right? So these two lanes are becoming it's not physically reduced, but some incident or something leads to closure of one of the lanes, right? So which means only one lane can be used for a duration of 30 minutes, right? So after 30 minutes the both lanes will be available. Okay, so that what happens? So the capacity is 1800 vehicles per hour per lane. So which means totally there is 3600 vehicles per hour is the capacity. But for 30 minutes, only 1800 vehicles per hour can cross. But the inflow, the demand is 3300 vehicles per hour. Okay. So first we'll draw the arrival curve. So the arrival is coming at a constant rate. So which is going to have a linear line. So this is 3300 vehicles per hour. Okay, so this is your arrival curve. So let's say this is V, and so it's just 3300. Okay, so this is your arrival curve. Now what happens to the departure curve? So departure curve is initially only 1800 is the capacity, right, for 30 minutes. So this is lesser than your arrival rate. Okay, so this, let us say the initial capacity is C1, right, for one lane. So this for how long it will be there? It will be there for T1 time. Okay, the T1 is 30 minutes. Okay, T1 is equal to 30 minutes. C1 is 1800 vehicles per hour, and V arrival rate is 3300 vehicles per hour. Okay, so what happens after 30 minutes? After 30 minutes, you have two lanes that are functional. So which means you will have flow happening at C2 rate, right? So which is two lane capacity, right? So C2 is 3600 vehicles per hour. So this is your arrival and departure curves, right? So departure curve, there is a change in the capacity after 30 minutes. So now when you have the arrival departure curve, so you can get different things. So the horizontal gap between these two curves is nothing but the delay experienced by a vehicle, delay for vehicle I, right? So if this is the value I, so for the ith vehicle the delay is nothing but the horizontal gap between the arrival and the departure curve for that vehicle. Okay, and the vertical distance, let us say this this vertical distance is nothing but q length at time t. Okay, if we take this as some time t, so the vertical distance between the arrival and the departure curves gives you the q length. Okay, and the area is equal to total delay, right? So basically you are summing up each individual vehicle's delay, right? So and so what will that summation be? It is nothing but the area between the arrival and the departure curves. So the area represents the total delay. Okay, and then so the number of vehicles affected is the number of vehicles where which experienced a delay. So in this curve, right, so if this is some value n, small n, so n number of vehicles, whatever is this n, where these arrival and departure curves are merging back, right? So that that point, whatever is the number of vehicles, so those many vehicles have got affected by this lane closure because all these vehicles have experienced some delay. Okay, so that this is the overall concept. Now we have to use the given values to come up to quantify these. Okay, so let's redraw this. Okay, so this is T1. Let us say when they are merging, this is point T2, and the number of vehicles at this point is N1. And once all the delay has been delay has become 0, let us say that is N2. Okay, so the first question is to find the maximum queue length, right? So where is the maximum queue length occurring? So I said the queue length is nothing but the vertical difference between the arrival and the departure curves. So visually, when you look at it between these two curves, okay, so the maximum queue length, so first initially the queue length is increasing, right? So when it is C1, queue length is keeping on increasing till the point T1 where the lane was closed. So that's when it has the maximum queue length, and then after that the queue length again starts to decrease, right? So when we want to find the maximum queue length, we want to find what is the queue length at time T1, which is when the lane closure is removed. Okay, so that's what we want to find. So how do we do that? So it's nothing but the cumulative count value from the arrival curve at time t1 and the cumulative count value at from the departure curve at time t1, right? So this that gives us the vertical difference, right? So how do we get that? So let's say this is n3. Okay, so n3 minus n1 will give us the maximum queuing. Okay, so what is n3? So the arrival curve equation is n is equal to vt, right? So and it passes through the origin. Okay, so this is the equation. So n3 is equal to v into t1. Okay, so what is v? V is 3300 vehicles per hour. Okay, into t1 is 30 minutes, right? So half an hour. Okay, so that is n3. What is n1? N1 is c1 into t t1, right? So because the slope of that line is the capacity for one day, so which is nothing but 1800 into zero point 0.5, right? So maximum queue length is equal to n3 minus n1, which is v minus c1 into t1. So that is 3300 minus 1800 into 0.5, that is 750 vehicles, right? So 750 vehicles are there in the queue, that is the maximum number at any point in time, right? So at any other time, if you measure the queue length, it will be lesser or it will be lesser than 750. Okay, so that's how we find the maximum queue length. It's a difference between the arrival, vertical difference between the arrival and the departure in the cumulative count. Second is total delay. As I said, the total delay is nothing but the area between the arrival and the departure curves, right? So which means we have to find the area between, this, arrival and the departure curves that we have here. So because this is not any, standard shape, so what we will do, we will make it easier and then divide it here, okay, at this point, and then convert this into two triangles, okay, and then find out the area of the lower and the upper triangle. So for this, so we need to find what is the, this particular length, right? So that will be the base of the triangle, and then this height also we need to find out, and then this height. Okay. So now first let us find what is the base of this triangle. So that is nothing but whatever is this time t3, and t1 minus t3 will give you the base, right? So what is t3? So t3 is where, at time t1 we know the number of vehicles is n1. Okay, n1 happens at t1, right? N1 also happens at t3 in the arrival curve, right? So from the arrival curve, using the value of n1, we can find what t3 is. So the arrival curve is n is equal to vt. Okay. So substitute n1 for n, and then t3 for t. Then we get t3 is equal to n1 by v. What is n1? N1 also from the departure curve. We know that n1 is equal to c1 t1, right? So this is c1 t1 by, okay. So that is one part. So the base of the first triangle is t3 minus t1. Now what is the height? The height is equal to n1, right? So that part is clear. This is t3, this is n1, this is n2, right? So far we have found out what t1, t3 is and n1 is. So we also need to find what is n2, right? So if we find n2, then the other part will also be fine. So, uh, so what is the equation of this curve? So that is n is equal to c2 into t plus a, okay? And we know that this curve passes through t1 comma n1, right? So we can substitute t1 n1 and find what is a. Okay, so n1 is equal to c2 t1 plus a. So a is equal to n1 minus c2 into t1. And what is n1? N1 is c1 t1 minus c2 t1, right? So c1 minus c2 into t1. So the equation of the second part of the departure curve is c2t plus c1 minus c2 into t1. Okay, and now these two curves, arrival and the departure curve, pass through some value t4 comma n2. So where do they intersect? So this is the arrival curve. So Vt equating those two, right? So this equation and this equation. So equation 1 and 2. So Vt is equal to C2t plus T1. Okay. So this T that is there in these two will be T4. Okay. So V minus C2 into T4 is equal to C1 minus C2 into T1. So T4 is C1 minus C2 into T1 divided by V minus C2. Right. So that is the time at which the Q dissipates completely, right? So what is N2 then? N2 will then be V into T4, right? From the arrival curve, substituting T4 in equation 2. Right? So N2 is V into C1 minus C2 into T1 divided by V minus C2. Right? So this is the total number of vehicles that are affected. So the height of the second triangle is nothing but N2 minus N1, right? So that is this particular height. Okay. So N2 minus N1. So which is the previous one, V into C1 minus C2 T1 by V minus C2 minus what is N1 is C1 T1. Right, so that is the height. So the base is same, which is T3 minus T1. So summing up these two triangles area will give us the total delay. So area, which is equal to total delay, is equal to, for the first triangle, half into T3 minus T1. What was that? So T3 is C1 T1 by V. Okay, T3 minus T1. So this is the base for both triangles. height is n1 for the first triangle, which is c1 t1, plus for the second triangle, it is half n2. The base is same, c1 t1 by v minus t1 into height is what we calculated earlier, n2 minus n1. So that is this big equation. So v into c1 minus c2 divided by v minus c2 into t1 minus c1 t1. Okay, so we can simplify this. Okay, finally what you will get is half into vt1 minus c1 t1 into c1 minus c2 by v minus c2 into t1. Right, so this is the total area between the arrival and the departure curves. So that is also equal to the total delay. Okay, so in this we know every term, right? So v is your inflow 3300, t1 is half an hour, right? c1 is 1800 vehicles per hour, c2 is 3600 vehicles per hour, right? So all the quantity is known. You substitute that, you will get the total delay is 1125 vehicle hours, right? So this is total delay not for one vehicle. This is experienced by all the vehicles, right? So that's why the unit is vehicle hours, right? So 1125. And the number of vehicles affected, so that we already calculated. So that is nothing but N2, right? So all the vehicles starting from the origin up to N2, they all have some delay, right? So that's why the total number of vehicles affected is N2. And N2 we know from this expression, right? V into C1 minus C2 by V minus C2 into T1. So that will give you 9900. And finally, we need to find the average individual vehicle delay. So how do we find that? So we know the total delay, we know total number of vehicles affected. So the average delay is nothing but the ratio of the two. So average delay is equal to total delay by total number of vehicles affected. So that is nothing but 1125 sorry 1125 divided by 9900, which comes out to 0.11 hours. So every vehicle between this time 0 to t2 has experienced on an average of 0.11 hour delay, right? So different vehicles individually they experience different delay, but on average we can say it is 0.11 hours. Okay, so that is all that we wanted to find. Okay, any questions, any doubts? So for this Q length and delay questions, so using the cumulative count curves will be an easier way of finding the answer. Okay, so use the given information to draw the arrival and the departure curves, right? And then your delay is nothing but the total delay will be the area between your arrival and departure curves. For at any particular point, the Q length will be the difference between your vertical difference between your arrival and the departure curve. And for any particular vehicle, the delay will be the horizontal difference. Okay, so that is all that you need to know to use the cumulative contours to solve these kind of questions. Okay, if there are no further questions, we will move on to next question, which is to match the transportation facilities in column X with their corresponding service measure in column Y. So we have three different facilities: freeways, two-lane highways, and signalized intersection. And the three service measures are average travel speed, delay, and density. Okay, so we want to match which service measure is used, for which facility, when we are doing this LOS, or the quality of service analysis. Okay, so three options are given. You have to choose the right one. Any answers? Which is the right matching? Okay, so let's look at the answer. So the right answer is option C. Okay, so what is the mapping? So one freeway is matched with C. So two with A and then three with this. Okay. So for freeways and also for multi-lane highways, we use density. Right? That is the measure service performance measure that we use for characterizing it. Right. So all the LOS would be the different categories would be based on the density. Okay. So that's what we use for freeways. For two-lane highways, again, so we said it's average travel speed, but it's not the only measure. So we have, as we saw in the introduction, we have three different measures. Average travel speed is one of them. Others are the percentage of the free flow speed and also the percentage time spent following. Right. So depending on the class of the highway that we are analyzing, the measure will change. But out of the options given here, the average travel speed is what we will use for two-lane highways. And finally, for signalized intersections, so we characterize the level of service in terms of the delay that is encountered, right? So just as we saw in the previous question, so there the delay was caused by the lane closure, but because of signalized intersections, signals also can cause delay, right? As we saw in the shockwave question, right? So when the signal is turned, the vehicles are stopping, right? So the queue length grows, so they have to wait in the queue, so that they are delayed, and so those kind of delays are used to characterize the level of service of the signalized intersection. Okay, so that right matching is in option C. Next question number 5 is we have to accept or reject the given statement. The Q discharge flow rate is the same as the post breakdown flow rate. Okay, do we accept or reject the statement? Any answer? Accept or reject? Okay, so the right answer is we accept the statement. The statement given is correct. Okay, so the Q discharge flow rate is same as the post breakdown flow rate. Okay, So in this, we saw when we were looking at the flow characterization for freeways and multi-lane highways. So we had like three different, flow characterization, right? So one is the undersaturated flow, and second is oversaturated, and third is your Q discharge, right? So undersaturated, right? So this is when your volume is less than capacity, right? So you have vehicles can travel at at higher speeds in the in the uncongested condition, right? So when volume is less than capacity, you have uncongested traffic flow, right? So they will be traveling at higher speeds, and oversaturated is in the congested state. Okay, so you have more than capacity, flow is more than your capacity, so you have congestion present in your facilities, therefore the speeds drop. Okay, and finally we have Q discharge. So Q discharge is when you are transitioning, when you are past, after congestion, right? So which also we call the recovery period, right? So which means the congestion, whatever was causing the congestion has been removed, and then the flow is now moving from the congested state towards the uncongested state, right? So that the flow rate at that time is called the Q discharge, right? So this is same as the post breakdown flow rate. So why? Because the breakdown is when this congestion is happening, right? So when the demand has exceeded the capacity, so that's when we call the facility has broken down, right? So it's not able to cater to the demand, and post breakdown is the same as the recovery period, right? So the flow that we see in the post breakdown flow is nothing but the Q discharge, right? So therefore these two are the same thing, right? So we accept this statement. Okay, question number 6 is determine the free flow speed of an urban freeway section if the base free flow speed is 70 miles per hour, and the data are as follows. Number of lanes is 3 in one direction, the lane width is 11 feet, lateral clearance is 3 feet on the right side, and the interchange density is 1.5 miles per 1.5 per mile. Okay, so here are the tables that you need for the different correction factors. For adjustment for lane width, this is for lateral clearance on the right shoulder, adjustment factor for number of lanes, and adjustment factor for the interchange density. Okay, so we have to use the adjustment factors from here, and based on that you have to adjust the base free flow speed to find the free flow speed for the existing condition. Any answer? Let's look at the answer now. So the right answer is the free flow speed is 58.9 miles per hour. So how do we do this? So what do we have? So we have the base free flow speed, right? So as we saw earlier, so the HCM, defines, these different, capacities, the free flow speeds, all for the base condition, right? So as we saw, base condition is the ideal condition, right? So you have, all these different factors are not affecting your, traffic flow. In that condition, what is your free flow speed? So that is the base free flow speed. So the base conditions, so as we see here, are given here. So for the lane width, so 12 feet, right? So that is your base condition. Because of that, there is no reduction in the free flow speed from the base condition. And then in your right shoulder lateral clearance is more than 6 feet. So again, that is also what we have in the base condition. The number of lanes, if it is more than 5, more than or equal to 5, that is one of the base conditions. And finally, the interchanges, the density of the interchanges per mile, if it is less than zero point 0.5, then you have the base conditions, right? When all these conditions satisfy, right? So that's the free flow speed that you can see in a freeway section. So that is your BFFS, right? And that is 70 miles per hour, for this facility. But what we have in the field is something different from the base condition, right? So we do not have 5 lanes, we have only 3 lanes, per direction. And the lane width is not 12 feet but 11 feet. The clearance is not 6 feet ideal as it should be ideally, but less than that, 3 feet only. And interchange also we have a higher density, right? So instead of 0.5 we have 1.5 per mile, right? So which means all these deviations from the base conditions should be accounted for, so when we are finding the free flow speed for this particular freeway section, right? So that's what is given in the different tables. How much is the reduction that comes when we are deviating from the base condition. Okay, how do we find it? So the free flow speed will be the base free flow speed minus the free flow actual free flow speed will be less than or equal to your base, right? So because base is from the ideal condition, so that is the maximum. So any deviation from it is going to reduce, right? So we have to subtract the reductions from the different conditions, right? So we have first for the lane width, then we have for the lateral clearance, then we have for the number of lanes, and finally we have for the interchange density, right? So all these factors have to be subtracted. So first, BFFS, we know it is 70 minus, for the lane width, what is the reduction? So we know it is 11 feet, right? So for 11 feet from the table, it is 1.9 miles per hour. And then for lateral clearance, so we have 3 feet of clearance on the right side. So for 3 feet clearance, so we also have to get the values for the number of lanes in one direction, which is 3. Okay, so in this column, so for 3, so we have 1.2, that is the reduction. And for number of lanes, so again we have 3, so that has a speed reduction of 3 miles per hour. And finally for the interchange density, so our interchange density is 1.5 per mile. So for 1.5, so we have a reduction of 5 miles per hour. Okay, so this gives us 58.9 miles per hour as the free flow speed for this facility. Okay, so in a base condition it will be 70, but because we have lesser number of lanes, lesser clearance, etc., so the vehicles cannot travel at the free flow speed that we expect in the base condition, right? So therefore the free flow speed for this facility is lower, right, which is 58.9. Okay, so next question number 7 is determine the level of service for the freeway section described in question 6, that is what we just analyzed. If the flow rate is 725 passenger cars per hour per lane during the peak 15-minute period. So here is the table that gives the LOS for different free flow speeds. Okay, so which means the free flow speed we have to take from the earlier problem, which is 58.9 miles per hour. For that free flow speed and this flow rate, what is the LOS? That's what you want to determine. Okay, so this should not be hard. We just have to use the table. to get the LOS. Any answer? Okay, so the answer is it is level of service B. Okay, but how do we get that? So what we have to do is, so we have to use the free flow speed. Also, so once we know the free flow speed, we will be looking at that particular section of this table. And then we also need to find out the value of the LOS criteria that we are going to use, right? So what is the service measure that we will use? So we will be using the density. Okay, so density we can get from the data that is given to us, right? So the maximum density. So how can we get that? So we know the flow rate during the peak 15-minute period, right? So during the peak flow rate is actually 725, passenger cars per hour per lane. So that is your flow, okay? And then you have to use the average passenger car speed, okay? Average speed, and then you use that to get the density. Density is q by s. Okay, so that's the relationship we know. So but we have the free flow speed but not the average speed. So what do we do in that case? So actually, so for these freeway sections, so there is a relationship between s and ffs. Okay, but if the if your q is lesser than 3400 minus 30 times ffs. So in that case, you can take S is equal to ffs. Okay. So what does this mean? Which means, so this is what representing a low flow condition. Okay. So when the densities are small, and your flow is small, which means that we are in the uncongested region. Okay. So if this condition is satisfying, which means that the average car speed is equal to your free flow speed, which means that every vehicle is traveling at the free flow speed, and this happens in the uncongested region. Okay, because the flow is small, the vehicle inter-vehicle interaction is also negligible. Therefore, all the vehicles can travel at the free flow speed. That's why we take the average speed to be equal to the free flow speed if this condition is satisfied. And for our case, 725 is lesser than 3400 minus 30 times 60, sorry, 59. Okay, so therefore we can consider the average speed to be equal to the ffs. But if this is not satisfied, then in the HCM we have the relationship that is given for s, that can be obtained from the free flow speed. Okay, but in our case we don't need that. So what is the density? It is q by s, which is equal to q is 725 and s is 58.9. So this will come out to be 12.81. Yeah, 12.31 actually. So that is the density. So we got the density, and now from the stable, so we can look at the stable and find it. So we are looking at 58.9, right? So as our free flow speed. So this stable, so we can look at this particular part, which is more closer, at 60 miles per hour. It's closer to 58.9. So we look at this proportion, and here for this first row maximum density, so we have 12.31. Okay. So for level of service A, so the maximum density is 11. Okay, for level of service B, it is 18, right? So 12.31 is coming in between these two. So which means that so it's not at level A, level B, but so it could be A or B, right? So in that case, we always go with the lower level of service, right? So if it is not either at A nor at B, so we will go with the lower level of service, which is level of service B, right? Which means that 0 to 11, we will take it as A. So from 12 to 18, we'll take it as level of service B and so on. Okay, so that's how we will read the table. Okay, so because it is between 11 and 18, we'll go with the lower level of service. Therefore, the level of service for this facility is B. Okay, so that's how we do the level of service analysis. So once we know the free flow speed and the density. Any questions? Okay. So moving on to question number 8. So here we want to do the same level of service analysis, but instead of previous segment, we are looking at the two-lane highways. Okay. So the following values of PTSF and ATS have been determined based on the analysis of 4 roadway segments. Determine the LOS if the road segments are 1, assuming they are class 1, 2, assuming they are class 2. Okay, so we are looking at 4 different segments, 1, 2, 3, and 4. So for each of them, we know what is the PTSF. What is PTSF? It is the percentage of time spent following. And second is ATS, which is the average travel speed. Okay. So these two quantities we know for each of the 4 segments. So you want to know what is the level of service for each segment. First, if it is class 1, second, if it is class 2. And this is the table which tells us what will be the level of service based on the performance measure. Okay. What is it for segment 1, class 1? Any answer? Okay. So as I said earlier, so for the two-lane highways, so we have 3 different classes, right? So class 1, class 2, and class 3. And for each of these classes, we use different service performance measure, right? So for class 1, we look at both the ATS as well as the PTSF, right? So both of these are used to determine the LOS. For class 2, only the PTSF is used. Okay, whereas for class 3 we use the PFFS, which is the percentage of the free flow speed. Okay, so different measures are used. So here we want to look at analyze these as class 1 first and then as class 2. Okay, first let's do for class 1. So assuming each of these 4 segments belong to class 1. So for first segment, so what is the PTSF? It is 36, right? Where does 36 fall? So 36 is between 35 to 50, right? So which means it is level of service B according to PTSF, right? So but we have to look at both PTSF and ATS. So with respect to ATS, so which is 54, so that is also saying that it is level of service B, right? So both are saying level of service B, so therefore the level of service is B for segment 1. So similarly we have to do for the rest of them. So for segment 2 PTSF is 54, right? So 54 is here level of service C, and then 47 is also level of service C, so totally it is level of service C. For segment 3, PTSF is 72. 72 is level of service D. And then ATS is 42. So 42 is also level of service D. So segment 3 is level of service D. So segment 4, PTSF is 90, which is more than 80. So level of service E. And then ATS is 30, which is less than or equal to 40. So that is also a level of service E. So LOS E for segment number 4, right? So in this example, so both PTSF and ATS gave the same level of service for each segment, but sometimes it may not always be that way. For example, if based on ATS you find the level of service is A, but based on PTSF you find say level of service is B. So in that case, what do you do when there are two conflicting level of service that you find from the two measures? So in that case, you always go with the lower level of service, right? So if one measure is saying a higher level of service, other measure is saying a lower level of service, the overall level of service you go with is the lower one. Okay. So if that is the case that you are encountering, but in this example, we saw that both measures gave the same, right? So there was no issue. Okay, so that is for class 1. So we have to repeat this with, assuming that all these segments belong to class 2. So for class 2, we have very simple because we need to look at only the PTSF, right? So ATS is not needed. So with respect to PTFS, so what do we have? So first we have 36. So 36 is between, so less than 40. Okay, so that is level of service A. So for segment 2, PTSF is 54. So 54 is between 40 and 55. So that is level of service B. Then we have 72 for segment 3, which is level of service D. Okay, and finally we have 90 for segment 4, which is level of service E. Okay, so what do we have? So what we find is the level of service for class 2 is either higher or the same as when we assumed it to be class 1, right? So for segment 1 it was level of service A, whereas it was B when it was class 1. For segment 2 it became B from C. For 3 and 4 it remained as D and E. Okay, so this tells us what? So as we say mentioned at the start of this session, so the level of service analysis is dependent on the facility type and also the mode, right? So for the same measure, so we are getting different level of service depending on the type of the facility, right? So if it is class 1, so we are getting a different level of service with the same conditions. With class 2, we are getting a different LOS, right? So again for the same condition, right? So which means our LOS, uh, you know, um, quantification is based on the type of the facility. Okay, so for class 2 it is acceptable, or you say it is the best condition even when 36% is the PTSF, right? But for class 1 that is not acceptable if it is to be the best, right? So in that case it goes to B, right? So it depends on the facility type. Okay, so that's the important. Okay, so that's all we had to do here. So here are the right options. So A is for class 1, B is for class 2. So they're the same as what we had in the previous table. Okay, so question number 9 is which of the following can be a surrogate measure for PTSF, right? So PTSF is percentage time spent following. So the options are time headway, average flow, density, and average speed. Any answers? Okay, so the right answer is option A. It is time headway. Okay. So why do we use that? So because see what is PTSF? As I said, it is percentage of time spent following, right? So which means on these two-lane highways, right? So vehicles, try to overtake, other vehicles, right? So and when is this overtaking possible? So it is possible when there is no, oncoming traffic, right? So if the oncoming traffic is also higher, if the flow of the oncoming traffic is high, so the number of opportunities that are available, for doing the overtaking will go down, right? So in that case, you will be spending most of your time following the leader vehicle. Okay, so you won't be able to overtake. So if this percentage of time spent following, other vehicles is higher, which means that your level of service is low, right? So because you are wasting your time or you're experiencing more delay by following instead of overtaking and then moving faster ahead, right? So therefore PTSF, if it is high, your level of service is low. But the problem is it is difficult to measure PTSF, right? So how much time each vehicle is spending when it is following, and how much time it is not when it is not following, right? So that can be difficult to measure. So instead of that, so we use a surrogate measure, which means it's an alternative, right? So this like correlates with PTSF. So if this is high, if this measure that we are going to have is high, then it means that PTSF is high, right? So that's a surrogate measure. So what can be used? So time headway is what we use basically. Not so how the time headway that we will use is the percentage of headways which is less than 3 seconds. So which means what? So what does a lower time headway mean? So time headway is nothing but the time gap between the corresponding points of the consecutive vehicles, right? So if you have two vehicles, let's say this is the front part, and there is a location here. Okay, let's say this is point A, the front point of this following vehicle is point B, and this is point C. So say this point A crosses location C at time ta, and this point B crosses this at time tb. Then the time headway is the difference between the times when these two crossed, right? So tb minus ta. So that's the time headway. So lower time headway means what? These two vehicles are following each other. Vehicle B is following vehicle A closely, right? So if it is close, then only the time headway will be small, right? So if these vehicles are far away, then the time headway will be larger, right? So if your headways is small, like less than 3 seconds, which means that B is following it, right? So it is following it. Is not in a non-car following mode. It is following vehicle. So if the percentage of all your headways, if that is higher, less than 3 seconds is higher, which means that most of the time is spent in following other vehicles, right? So that's why this PTSF and this lower time headways, they will be correlated, right? So higher number of smaller headways means more time is spent in following the vehicles, right? So that's why we can use the time headways as a surrogate measure for PTS. Okay, so the next question is, higher speed is expected in class 3 two-lane highways compared to class 1 two-lane highways. We have to either accept or reject the statement. Any answer? All right. So the right answer is option B. We reject the statement because it is not correct. Uh, so why? Because what is class one? Class one highway is in the rural areas. Class three is when it is in an urban environment. Okay. So what do we expect? So in urban areas, we expect lesser speed, than in rural area because there is more external factors that come into play in the urban setting, right? So you'll have more number of intersections, higher flows, etc. So therefore the speed will be lower. That's what we expect also. So we do not expect to travel at higher speeds in urban regions, whereas in rural regions, so we expect to travel at higher speeds, right? So therefore class 1 should have higher speeds than class 3, right? So that's what we expect. So this will also affect our level of service measures, right? So that's why there will be differences in the level of service criteria. So therefore this statement is incorrect. So we are saying that the reverse of this, so therefore this is an incorrect statement. So question number 11 is, when a facility is operating at or near its capacity, what will be its level of service? So options are A, C, F, and E. Any answers? Okay, so the right answer is option D, it is level of service E. Okay, so why is that? So what do we know? So we know like A is here, best level of service. F is the worst level of service, right? And when does level of service F occur? So level of service F occurs when volume exceeds capacity, right? So this is also the breakdown condition, right? So a facility is breaks down when its demand exceeds the capacity, right? So when the facility is no longer able to serve the demand. Okay, so in that case, we call that level of service F, right? So demand is higher than capacity. So before the breakdown occurs, so because at breakdown we know the volume has the demand has exceeded the capacity, right? So when will the demand be equal to capacity? It will be just before the facility broke down, right? So before it reaches level of service F, it would have been at the capacity, right? So after reaching the capacity, then only it would have exceeded. So that happens in level of service E. So E is at capacity. So when it is at capacity, so that is the maximum that it can serve. Okay. So once demand exceeds this, so it will become even worse, and then we will reach the breakdown condition. So at E, level of service E, we will be looking at capacity or near capacity, because this levels of service, it does not change at a point, right? So it is defined for, it's a step function, right? So until some value, the allowable service will be something. So once that exceeds, allowable service will suddenly become another value, and that level of service will be maintained for another range of the service measure that you are looking at. Then suddenly it will change to C and so on, right? So there, because it's a step function, so therefore, so it will be at capacity or near to capacity, we will be having level of service C. right? So, but once it exceeds, it will become into level of service F, right? So, because here we are looking at or near the capacity, so it will be at level of service E. Okay, any questions? So with that, we are coming to the end of this week's session week number 4. Okay, so if you have any doubts or questions, you can ask. Otherwise, we can wrap up today's session. Okay, in the meantime, till our next session, you can make use of the discussion forum in the Swayam portal to ask any questions that you may have. And yeah, so with that we can close the session if there are no questions, and we can meet again next week, Saturday at 4. Thank you for attending.